I've mentioned conferences a couple times on the channel. The very first conference I went to was in Fargo, North Dakota. We traveled with a large group of people, and it lasted a weekend, and it was really fun. The second conference I went to was in Banff, Canada, which is outside the U.S., clearly, and it lasted a full week, and it was thrusted upon us at last minute, meaning that we had to decide within the day that we were going to go and then prepare for travel in like 2 days because that's when the plane took off. It was really fun, and I'm really glad I did it, and I want to go back to Banff someday because it was a beautiful city. In fact, my friend that went with us, I think he wants to move there after leaving. He didn't want to leave. I can't blame him either. But the third conference I'm preparing for now is a bit aggressive because I say aggressive in the sense that this conference is taking place in Spain, which is in Europe across the Atlantic Ocean. And this is a huge move for someone like me. I'm not really comfortable. I'm more comfortable traveling these days, but this is across an ocean. And I feel like if other people in the math department, like the international students that come to the U.S. to get their PhDs, if they can do it, then certainly can I. Because I've never traveled to Europe before. I've never traveled across an ocean before. I want to do more traveling like that, but again, it is expensive, so it's kind of like, it's just a matter of when, not like if, when you have the resources to do something like that. But I really want to go. I really want to see Spain. I'll be glad when it's over. It'll be such a great experience. While I'm there, I want to buy some souvenirs. So I don't know if you guys, I don't think I've really mentioned it on the channel, but I tend to buy hats. I like to collect them from different locations. Like I got this one from Sequoia National Park in California, as well as my Yosemite hat from Yosemite National Park. My Coke hat is my favorite just because it fits well. I got it from Orlando, Florida. And then I have my Banff cap that I got in Banff. I didn't get anything from North Dakota, now that I think about it. Oh, that kind of sucks. But anyway, I got a Grand Canyon hat. My friend who traveled to Seattle, Washington, got me this. I've never actually been there. And my Skull Creek hat from South Carolina. So I like to collect these. They're nice little trinkets from places I visited. But I also have to buy a souvenir for someone very special. I hope she watches this, and I hope to give, I don't know what I'm going to buy her, but I'm looking forward to giving it to her on that August day. But anyway, that's what I'm going to do in Spain. I got some souvenirs to buy, and I want to talk a little bit about math because otherwise this video will be pointless. So let's talk a little bit about math. What I want to talk about is how I read a math paper and take notes over it. Because different math papers will be written in a different way, and I want to make sure that when I read it, I understand something, because it can be kind of daunting to read something that's written in someone else's, I'm not explaining it well, but the idea is that this paper will make a lot of sense to the people who wrote it, and the people that are reading it don't really have the same background typically, or are not as comfortable with the computations and the explanations as the authors that wrote it. So you have to spend some time rereading it and making sure that you understand it, so that when you write it in your own language, you can recite it to someone that may not understand what's going on here. So the paper that me and my advisor are reading right now is called Analysis and Geometry Near the Unit Ball, Proofs, Counterexamples, and Open Questions. And they talk about a couple different open questions here and some stuff that they've done. They kind of study convex bodies that are close to the unit ball in some sense. And what I'll do, if the paper is written pretty well, which this paper is written pretty well, it's very comfortable. I've seen a lot of this stuff before because we talk about it in the department quite a bit actually, is that I'll bust it up into different sections. So what I'll do is I'll start with the introduction. I'll read it. There's not really any math in the introduction. It just kind of prepares you for what's to come. And then when I write it on my sheets of paper here, I'll write introduction, and then if there's no real math, I'll just say, okay, we're just going to be talking about perturbations of the unit ball, meaning that our convex body is close to the unit ball within some metric. And the metric that we use typically is the Banach-Moser metric, or the Hausdorff metric. So I'll just make a notation, or that B will represent our Euclidean ball in Rn, and proceed from there. And then as you can see, I go straight into section 2. So after I'm done reading section 1, what I'll do is I'll start with section 2, notations and observations. And here, I like sections like this because all they really do is just set you up for the real math to come. It kind of makes you feel like you're learning something, even though really you're just writing down definitions. It may kind of feel, that's just me. A lot of people say like, they actually like doing the math as their favorite part, but I like the phase right before the real math where you're getting ready and writing down your definitions, because I can do that. I can do definitions pretty well. Solving problems, not so much. Memorizing definitions, I can do. So I'll write down what's important, like convex body, containing the origin in its interior. I'll write down the definition of radial function, the definition of support function, and then I'll draw an example, and you can see, you know, what it might look like, for example, if you want to visualize it, because everything here is geometric. I should be able to draw a picture that's reasonably good. And I'll make a little remark off to the side, like, I remember from class that the radial function never exceeds the support function for any convex body. And if the radial function and the support function are identically equal to one another, and you can normalize it, say it's equal to 1, for example, then you can conclude from that, from there, that the convex body in question is the unit ball. In fact, that was a homework problem that I presented at the board last spring semester. In fact, I made a video about it called the Blaschke-Santalo inequality, which someone managed to explain in the comment section, so I'm very grateful for that. So I'll write down some more definitions like E perp, the definition of the hyperplane orthogonal to E. And then we have the Hausdorff distance, which I've written here. This definition of Hausdorff distance is a little bit different from the one that I'm familiar with when I was presenting a paper that involved this distance that they're talking about here. But it's a perfectly legitimate definition. So what it says is the distance between a convex body K and a convex body L is equal to the infimum over all positive R such that K plus RB, so this is the Minkowski sum between the convex body K and the ball of radius R centered at the origin RB, contains L, and L plus RB contains K. So to help visualize this, I drew a picture. Let's say that K is equal to the square, and our R ball is this little sphere that I've drawn. Then K plus RB is just, you take K, and then you take like this circle, and see what shape you get when you trace out the circle around the boundary of K, where the center of the R ball is at a point along the boundary. So this is what K plus RB looks like, and it gives us this square, and the idea, well, this rounded square. And the idea is that you want to choose R small enough, the smallest possible R that you can choose, such that L can fit inside here. Obviously, if R is huge, then you just get this massive shape that L can fit inside of, but that doesn't really mean much for us. We want to choose the smallest possible R that we can still fit L inside. And that will satisfy the first condition here. You obviously have to do the same trick for L, where you take RB and trace it around L and choose R in such a way that K can fit inside. And when you take the infimum over all possible R that satisfies both of these conditions, that's what we call the Hausdorff distance. So when we talk about a convex body K being close to the unit ball, what we're saying here is that for some epsilon small, meaning between 0 and 1, we want to effectively sandwich K in between this slightly smaller ball and the slightly bigger ball compared to the unit ball centered at the origin. So that's what we mean when we say K is a perturbation of B. And then I have a little discussion on isotropic position. I'm pretty sure I did not write this down correctly, so feel free to chastise me in the comments about what it was, because I read it and I thought I understood and I wrote this down. I was like, wait a minute, this doesn't make sense. I need to go through this again, because this is what we're going to talk about with my advisor tomorrow in our meeting. We're trying to prepare. What we're doing is we're trying to prepare for the candidacy exam, which effectively I'll just give a presentation over something smart that I want to prove. And I don't really know how much is necessary. That is kind of something that my advisor decides for me. And once he decides, like, okay, you understand the situation good enough, then we'll do the candidacy exam and you can stop taking classes finally and go on dissertation, which I'm looking forward to. All right, so then we transition into a discussion on spherical harmonics. This takes a while to unpack. I remember this took us there was probably a week in class dedicated specifically to this. Hold on, I need to check how much time I have on my phone because I think my battery's about to die. Well, okay, we'll finish up here. It'll be a relatively short video. But if you want to read it, you can pause the video and see what I've written. But essentially, we're doing some sort of linear algebra mumbo-jumbo, being able to decompose a polynomial into a sum of polynomials that look like this, where these polynomials come from this space of harmonic homogeneous polynomials of degree m, orthogonal complement, and blah, 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 blah. It's a lot of work to show some of this stuff. But effectively, all this work, I'm saying effectively a lot, but what we do is we want to build all this machinery so that we can finally say the following. For an L2 function f that's defined on the unit sphere, we can decompose it into a sum of functions f1, f2, f3, so on and so forth, where each of these functions fm come from this class of harmonic functions hm, where each hm is pairwise orthogonal. And the reason we do it is because it's a nice tool that helps us solve problems in convex geometry. That's really all it is. And then we go into spherical Redon transform, which should sound familiar because we talked about it in our Fourier analysis class. So there's a lot of review from Fourier transforms here. I'm not going to go through it because it's a lot of machinery. It takes a while to explain. What do I really want to say? I guess we'll get down to the bottom here. We'll just define what spherical Redon transform is. So for an L2 function f, what we can do is we say that the Redon transform of f evaluated at E is the integral of f with respect to the n-2 normalized arc length measure around the boundary. It's n-2 dimensional, but think of it in R3. This is what my advisor always says. In R3, this gives us the normalized arc length measure, and we integrate around essentially the equator, where this equator is, it's on the sphere, it's on the unit sphere in R3, and E perp is that plane that gives us that equator. So you're effectively trying to find the average value of f along that equator. And if we have the definition of Redon transform, we can actually decompose it in terms of the harmonic decomposition of f, where it's just equal to the sum of these coefficients Cm plus the functions fm from those class of harmonic functions. Which is kind of nice, because here we have the decomposition of f, and all it's saying here is that if you take the Redon transform, you just throw in these coefficients times f and do the summation again, which those coefficients, it requires some explanation, but this is what they look like. I remember deriving this in class. It's kind of a little scary and takes a while to explain. More stuff. And then we finish section 2 with a little discussion on bodies of revolution. The reason I included it here is because a lot of times when you're asking questions like, okay, do convex bodies have this property X, Y, and Z? And you may not be able to make any progress on it. But what I have found is that a lot of my instructors that do research here, what they'll do is they'll restrict their attention to a smaller class of convex bodies, which are bodies of revolution, which I've defined here. You can pause it. It makes a lot of sense if you think about it. You have this function that's concave, the two endpoints agree with one another, and then you just kind of rotate it around your favorite axis, and then boom, you get a body of revolution which is convex in nature, provided that the function makes sense. And then I provide an example. So, like I said, the problem that me and my advisor are talking about involves the Bousman-Petit problem. I'll let you pause the video and read what it says here. But this is the problem that me and him have been investigating, and hopefully we want to take this question. We have some sort of partial result for it, which is stated here. If k is close to the ball, then we know that k is equal to the ball in Hausdorff metric. We have this idea of what to do with this problem that has already a partial result, and we want to effectively give like a corollary to it, where we're looking at floating bodies, which I know I'm not explaining what floating bodies here, but this is what I want to do my candidacy over. And if I can do that, then I can finally be on dissertation and finish what I started so many months ago when I finished my qualifying exam. Okay, so this was a hot mess of a video. Thank you if you made it this far, and I'll keep you updated on the measure theory review in the near future. Thank you, goodbye.